Hello again, and welcome back to the second part of Chapter 16, where we talk about the immune system and how it protects us from everything trying to kill us or get in there. So, fun stuff. So anyway, we're going to be talking about T cells and B cells. Remember those lymphocytes that we talked about way back in Chapter 13? 14. And we're now going to talk about the other half. So, if you've ever been sick and you go to the doctor, sometimes they'll palpate around your neck because what they're looking for is a swollen lymph node. Because remember, these guys are hanging out in your lymph system. And remember, as I said earlier, your lymph nodes are basically the security checkpoints of your body, especially for the immune system. And if you get an infection or you get sick, your lymph nodes will swell up because that means it's the site of a battle and all the white blood cells are just absolutely fighting for your life. So when you get sick, sometimes your lymph nodes will swell up. So that's why when you say, I'm sick, and your doctor starts doing this, he's looking for swollen lymph nodes. For instance, my favorite was when I was way back in time, dinosaurs ruled the earth, and when I went to high school, which doesn't seem that long ago to me, but okay. And it was kind of crazy. I got sick with foot and mouth disease, and my lymph nodes were huge. I felt like poop, but my mom sent me to school anyway because she was one of those moms. And I just said, I feel terrible. And I fell asleep in marching band. And that's when I knew something was up because you don't usually pass out in marching band. It's just not a place that's conducive to sleeping in class. So I knew something was up. And she drugged me to the dentist going, we got to go to the dentist. And I'm like, Mom, I don't think I should go. I'm feeling really bad. And they're like, what? And so they bring me to the dentist, and the dentist takes one look at me, and she goes, no, I'm not seeing her. She's sick. Get her to a doctor. Why did you even bring her here? And yeah, my lymph nodes were huge, and you have to take like horse pills of antibiotics to get this down. I was out of school for a week. And before that, I was so mad because I was on track to have perfect attendance that year. I've never had perfect attendance, but I was so close, and then I got attacked. Oh, well. So, when we look at defense against pathogens or disease-causing agents, there's two ways your body generally defends itself. There's innate or non-specific defense. This is general responses like mechanical barriers. Your skin is one of them. Chemical barriers, natural killer cells, which are really cool. Inflammation, fever. So your main one is your skin. You don't want people really to get past that. And the next is your hair and your cilia, your mucous membranes. That's why all of our openings from the inside of our body to the outside has a lot of mucus. Same thing with upper nose. Why we have earwax. Because all those secretions actually slow things down because things get stuck in them. It's a mechanical barrier. That's, why we have nose hair. It's why we have ear hair. It's why we have earwax. It's so that way things that are floating around, if they get in, they get stuck up in the wax, and we secrete that all the time. And bada bing, bada boom, it's stopped right there. That's actually our best defense is our ear hair, nose hair, and mucous membranes, and earwax is actually the best defense we have against fungus. That's because once a fungus gets in your body, it's insanely hard to get out. And I'm not talking about athlete's foot. I'm talking some major fungi. Fungi stay out of us unless it's on a pizza. Then I'll eat it as long as it's cooked because I like mushrooms on my pizza. If you don't, that just means more mushrooms for me. Anyway, and I'm sure there's something you like that I don't like, which means whatever that is, there's more for you. That's kind of how I see that. Anyway, digestive enzymes in the mouth, stomach acid. So if we eat something bad, looking at you, Arby's, our stomach acid can take care of it. So, if something we actually accidentally ingest something that should not be there, usually, a pH of 2 and a whole bunch of really active, excited enzymes usually take care of it pretty quickly. If it doesn't, something's up. Anyway, internal defenses. We have inflammatory response. So remember we talked about getting cut and how that inflames this area, which is actually pushing things back together. Complement proteins, phagocytic cells, and my friend, the natural killer cell. And he's cool. He's insane. He's basically a cell that's pre-programmed to go around and just literally stab something with some digestive enzymes and let it die. They're literally out to kill anything and everything that doesn't look right to it, which is anything that's invading and even our own cells that may be ailing. So if one of our cells is sick and it's actually broken one of its proteins on the surface that lets it know that it's sick and it can't carry out apoptosis on its own or programmed cell death, the natural killer cell literally comes over and pokes it and kills it. And then he goes on and finds somebody else. So imagine, you've got some cells running around with a mini version of a knife just ready to stab. So that's our natural killer cells. Are they not insane? Isn't that crazy that you've got like murder cells running around in your body that, just kill anything that it doesn't like or our own cells that are like, help me. And it's like, so fun. Anyway, then you've got your adaptive immune system. So this is where the antibodies come in. Remember, we talked about antigens and antibodies when we talked about blood transfusions and all that fun shenanigans. Now we're going to talk about it when it comes to things like invaders like, our friend COVID-19 here, or when we get bacterial infections like our friend, the Black Death right here, because he was actually a bacteria. We actually have new models that rats didn't actually bring these guys around. It was actually human-to-human contact because we were so adorably dirty back then. Yeah. Which is really fascinating to go into the Black Death and the waves that it actually gave rise to the middle class. Because before that, it was either serfs or nobility, and there was no in between. There was like no in between. And after the Black Death went through, it really equalized human society. It's amazing what insane impacts that huge amounts of epidemics and pandemics that go around have on us. I mean, we're in the aftermath of the COVID-19 era, sort of, kind of. Hopefully it doesn't have another flare-up. I'm just saying, we're probably still going to be studying the impacts for years on end on just what 2020 did to us. Dang you, 2020! Anyway, it's supposed to be a good year, and you betrayed us. Anyway. So that brings in the cell-mediated immune response and a memory response. We're going to get into that. This is just the adaptive immune system, which is your immune system, is just absolutely amazing. I will probably geek out here. So anyway, innate species resistance, measles, mumps. Interestingly enough, I know other animals don't get that. Monty, like for instance, if I get sick with a cold, he's not going to pick it up because he's a snake. It does, there are some diseases that will jump between species, but that's only because if you're living with the species way too intimately. And I don't mean, in that way. Get that out of your brain. I mean, like, if you're living with, literally, you walk outside and there's your cows right in your face. Like, way too close. Because one of the first diseases that jumped to humans is actually because we domesticated cows. And we were living very closely with cows. Like, you had your hut and then you had your cow pen. So things jump really easily when you're living next to a bunch of species that are pooping and peeing everywhere, and it's not exactly sanitary. So that's actually where the oldest of one of the diseases, and I'm going to get into this a little later. I think I added it to these notes. That's where measles, smallpox. Thank you. Sorry. Smallpox. Smallpox came from cowpox. So one of the first major diseases actually arose from literally us making the original civilizations that gave rise to the civilizations that we know today. That's where it came from. Us domesticating cattle and living way too closely with them in poor sanitary conditions. And then bada bing, bada boom, cowpox mutates into smallpox. And we'll get into that in a minute because that actually, we'll talk about vaccines because they're just fascinating again to me. Okay, so mechanical barriers, as I was mentioning earlier, skin, mucous membranes, it's your first and second line of defense. Chemical barriers, gastric juice, interferons, defenses, collectins, these are guys that are going around. They complement our immune system. And then we've got our natural killers. Like I said, if a cell gets infected, these guys come poke them with an enzyme that kills them. So like I said, guys running around with a little enzyme knife going, come here. Inflammation, which remember, as I said earlier, if you get cut, whenever the cell dies that it's not supposed to die, it releases chemicals that call in the white blood cells going, I have died in vain. Avenge me, my brothers. And the white blood cells come in going, yes, we will kill them all. And then the phagocytosis can be free or fixed. Those big monocytes that come in, fever, which is basically kind of like our version of a nuclear strike. Fever is kind of, our body does it, and it's done by the hypothalamus. Because the hypothalamus goes, well, if I just turn up our internal temperature to the point that it should kill everything, everything should be dead. The problem is that works on us too, which is why fevers, we try to bring that down instantaneously, because it's your hypothalamus going, I'm just going to kill everybody, and hopefully we'll live because there's more of us than whatever's infecting us. Which is kind of a dicey thing to do. So that's kind of why a fever to me is kind of like the analogy is a nuclear bomb. Because it's kind of something that's just like an all or nothing. It's like if we're going to, we're going to take you out with us. So, yeah, it's kind of a blitz attack. It's not very well orchestrated. Thanks, hypothalamus. Rude. So that's why we usually instantly, give you drugs to bring your fever back down because, yeah, the fever could kill off your infection, but it could also kill you. So, all right, again, we just talked about all this. We'll get into it in a minute. I'm just showing you lots of pictures because pictures. Again, he does a good job of going over your innate defenses and how that all works, and you should see his animation for the natural killer cells. It's kind of cute. Highly recommend just because of the animation of how the natural killer cells look. They're cute. All right, so this is where we get to talk about the adaptive defenses or the immunity. This is where it's fun. So this is where we break it down into two parts. You got your humoral immune response, which are the B cells, and your cellular immune response and the T cells. And they do work together. But we're going to talk about B first and then talk about T. But keep in mind, I talk about them separately so you understand the differences between them, but they work together like, peanut butter and jelly. So especially since B cells will call in T cells to help them out. So remember, these guys are best buddies working together. So your immune system, remember, as we talked about this when we talked about blood transfusions back in chapter 14, is this. Your immune system needs to know what self and non-self is, and that's where we get antigens or foreign, and that's where we get those protein flags. Remember, I talked about those protein flags that are all over your thing, and the white blood cells come through and check. Like, for instance, I'm just going to use COVID here, just like with your red blood cells. You got the A antigens, the B antigens, or the AB, or if you're O blood type like me, you don't have any antigens, so none of these little guys sticking up. Okay. So we have our own little protein flags called antigens, and if they're healthy and whole, that means the cell's doing his job in your body, and the immune system checks it and says everything looks good, bye, and everything's awesome. So that's basically how your body figures out what is self and what is non-self by these protein flags, by these antigens, which is actually how we're getting really clever with vaccines a little later. I'll get to that in a minute. So anyway, so these antigens are the flags that let your immune system know that this is me and I can't kill me because that's bad. Okay? All right. Now, there's ways that can get completely screwed up, but we'll get there anyway. So again, where do these guys come from? So the B cell, again, is made in the red blood marrow, and he goes from the blood. He's transported after he grows up, and he matures and hangs out in the lymph nodes. So that's, again, why we talked about lymph first. So he hangs out in there. Sometimes they wander around, but for the most part, they like to hang out in the lymph node. Now, the T cells, again, made in the red bone marrow, but they go to the thymus. Remember, that's that organ behind your sternum right here that shrinks as you age, and they mature in here. So these guys, remember that T4 and T3 hormones we talked about? Yeah, this is where that comes back into play. So the T4 and the T3 hormones basically stimulate these T cells in the thymus to mature into full battle-ready T cells, ready to fight. And they also go out through the blood system, and they're all a lot of travel, but a lot of them end up in the lymph node again. Like I said, the lymph node's airport security, so they're all hanging out there. But they're also traveling around too. So that's the two journeys. The B cells literally just go from red bone marrow into the lymph nodes, whereas these guys go from the red bone marrow into the thymus, mature because of the T4 and T3 hormones. And then when they're ready to do battle, they go down into the blood system, the circulatory system, and the lymphatic system. Okay? All right. So that's where they come from. So let's talk about the humoral immune response with B cells. So we're only going to talk about B cells right now. So let's leave the T cells out of it because they can do some funky things. So B cells are actually, again, they're kind of a primary response guy. So say something comes in, like a new virus, and I'll just use him here because he's here, and he comes in, and again, he's just like, nothing to see here, I'm not really a virus, and a B cell catches him. Now you'll notice he has his own protein receptor sticking out. Think of like these guys coming out, and they have a whole bunch of different ones. Every B cell is slightly different, unless it's later on down the road. So think of it kind of like, one of these Swiss Army knives. They just come with all of these different proteins sticking out. So that way, I know I have a lot of keys, but I have a push button car, so don't yell at me. I've had so many people yell at me, go, "You're gonna hurt your car's transmission." I have a push button. This is my second push button car. Please stop yelling at me about this. Anyway, so as you can see, he has like this, a Swiss Army knife. It has a lot of different things. And it's the same thing with the bees. They have a ton of these antigen binding receptors, and they're all different. And so it's kind of like he has like a bunch of keys. So he goes up to it, and he's just like, well, does this match? Does this match? Does it bonk? Oh, it matches, and it triggers. It triggers him, and he goes, "Whoa, I've got a bad guy here," and he starts turning into different types of B cells. So he turns into ones that do nothing but make that one antibody that binds to whatever comes in, whether it be a bacteria or a virus. So it binds to him, and he goes, "Whoop," and he starts replicating. And then most of these guys start pumping up antibodies. But out of these guys, one of them will pop into a memory B cell, and he will be somebody who will remember this for later if it comes in the body again after you survive the initial attack. So these guys are pumping out antibodies, and it clumps these guys up. What it does is it sticks to these guys, whether it be a bacteria or a virus. It stick, and it glues them down, and it clumps them up. So a bunch of them will get clumped up together. So it's kind of like, sticky paper, except insanity. Have you seen, I don't know, the first Incredibles movie? There is a scene where he's running through. Here, let me see if I can pull it up real fast. Let me see. YouTube. Yeah, YouTube. Sneaking in? Yeah, sneaking in the base. Bob sneaks in. He gets caught at the end. I'm going to see if I can find it. Skip ads. We do not need you. Yeah, this is him sneaking in. Now, I need the one where it's like he's running in. Incredibles, Bob gets caught. Maybe that's it. Bob gets caught. Yeah, this is it. This is kind of how I remember, how I think of the antigens attacking. Hold on, let me just zoom in. Yeah, there it is. Yeah, so yeah, this is kind of how I think of antigens. So he's getting stuck and see these things stick to him and is like, he's getting stuck to it. That's how I see antibodies sticking to a virus, is this right here. Yeah, there you go. So that's basically how I see antibodies attacking a foreign body in your body. It just glues them down so that way another white blood cell, usually like a monocyte, will come in and just go munch, 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 and eat it up. So there you go. So that's kind of how I see that. Let's go back here. So that, I should put this little clip in here. But that's basically how I see how all these antibodies work. Is they just glue themselves to that. And therefore, that's how we fight off invaders like viruses and bacteria, through the B cells. So this is B cells, okay? So this is what B cells do. So they make all the antibodies. So when you hear about, making the antibodies, it's the B cells that make all the antibodies. And like I said, they're like Swiss Army knives. They come out with all these different antigen receptor sites that are so different. And everyone's born with different ones. And it just depends on the right combination. And it's amazing. Our DNA actually codes for like millions and millions of different types to build this. So it's insane. The math of it is just astronomical. Our immune system is capable of pretty much coming up with all these different ones to just randomly find the right one for certain viruses. It's really amazing. Now, years down the road, say, you get sick again and this particular bacteria or virus gets in, well, that's your secondary response. Okay, your secondary response like spikes instantly. The minute anybody finds something, the B cells instantly, they don't even waste time. They don't even waste time trying to figure him out. They already know him. They've got his number. So they instantly just go whoosh and turn into a whole bunch of plasma cells pumping out those antibodies. And again, it refreshes the B memory cells as well. So it not only refreshes your immune system to remember down the road, but it also makes these guys just absolutely explode and takes it out. And you don't get sick. You don't really feel it. So, yeah, you get sick here, and then your immune system remembers it, but later on it comes in again, takes it out like that because it remembers. So that's the humoral immune response with your B cells. Now let's talk about the wacky nutcases of this T cells. Again, he comes in and talks about these guys, and they're a lot of fun. So if you want to learn more about the B cells, watch this one. He does great animations for these, or whoever does the animations. So again, primary immune response, secondary immune response, you can see how exponentially it just explodes, which is why, we actually use vaccines. We'll talk more about that in a minute. So again, first exposure, it takes days after exposure. So again, it takes a while for your body to A, identify it, B, ramp up production to take it out. And then that's why you get sick for a while and you feel like, bleh, and then so that's why we get sick first time around. However, second time around, you don't get sick anymore because if it even remotely comes in, the B cells just go crazy and boom! Now it makes a high concentration. Hold on. Excuse me. And 1 to 2 days, and antibodies remain for months or years, and the memory B cells live on for pretty much years. So, yeah, that's why, once we got your number, we got your number. So, that's the B cells work when something bumps into them. However, what if the antigen gets into a cell? What if they do a Trojan horse thing, and they go, haha, I'm going to get into a cell, and therefore you can't see me because I'm wearing this cell's body, haha. Well, that's where the T cells come in. So the T cells, just like the B cells, there's many different flavors, but the two we really need to know are our helper T cells, which are the watchdogs of your immune system, and the cytotoxic T cells, which are the stone-cold crazy killers. So the helper T cells, and unfortunately this is where HIV gets you, HIV will kill these guys. And then you don't have eyes on your immune system, which leads to your immune system not knowing anything's wrong, and you die from a flu that would otherwise you would not have died from. So, yeah. So HIV kills these guys, which is bad, which is why it's an immunocompromised disease. It will destroy your immune system because it knocks these guys out. Because what these guys do is they pretty much are on the lookout for any cells looking suspicious. And some cells are actually pretty cool. Like, for instance, the big macrophages I keep talking about that go around, nom, 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 nom. If they hit something that's not normal and they eat it, what they do is they actually break off these antigens. They pull them off and then put them on their own head. And then they go up to a helper T cell and say, hey, check this out. And the helper T cell goes, oh, that's something new. Thank you for bringing this to me. And then he starts going crazy, and we'll talk about that in a second. So other macrophages literally will go in, kill something, and then take what's on the, like, for instance, this is COVID-19, all these little antigens right here. They will literally rip these off, plop them on their own head, and then go show it to a helper T cell. And the helper T cell goes, oh, this is new. We need to be on the lookout for this thing. And gets that whole story going that we're going to talk about in a second. Other ways is, like, again, cells will, like, the killers, if they're sick or something, they'll break their own proteins, and the killers will come in and poke them and kill them. But also the same thing here. If a helper T cell sees a cell that's been invaded and he's not looking so good and his own proteins are broken on the top, he goes, wait a second. So he's the kind of the eyes and the ears of your immune system. But if he's taken out, then the immune system doesn't know anything's wrong, and they don't get triggered. And that's why HIV kills when it turns into full-blown AIDS. So say something comes in. So again, what happens is the B cell, he goes crazy, and he starts making a ton of these antibodies. We just talked about him. Well, the T cell, the helper cell, is really interesting because he actually goes and he'll talk to the B cell. The B cells actually bring in helper T's, going, hey, helper T's, come on over, man. I think we found somebody, and I'm going crazy, making antibodies. And the same thing, macrophages will go to a helper T2 to get checked. He'll eat something and be like, that doesn't taste like it's from around here. Rip off those antigens, put it on his head, and go over and get checked. So that the helper T also will yell out and get in all the rest of the white blood cells that need to come in. So, like, the more macrophages, more neutrophils, more eosinophils, all those fun guys I talked about in chapter 14. So anyway, again, same thing. He'll go into, now these guys are then turned into, they'll make T cells. So what these T cells do is they actually so the T cells are cool. So again, like I said, here's a macrophage. He eats something. He grabs the antigens off. He puts it on his own surface. He goes up to a T cell, and usually a helper, and he goes, check this out. And the T cell goes, oh, and then he starts going, woo, and then he splits into many multitudes of 4 different types. The killer, which is trained to literally just go out and find that foreign whatever it is and kill it, period. So they're just roves of just murderous white blood cells out to get this one thing. So, then the helper T cell, which stimulates more of these guys to go check it out, and more B cells to start going, make a bunch of things, make a bunch of antibodies, make a bunch of antibodies. Suppressor T cell. So these guys inhibit T and B cells. And because, unfortunately, if your immune system isn't stopped, it can actually do a lot of damage. And we'll talk about how COVID-19 was doing that. And then again, memory T cells. So again, so we can remember it for later if we run across it again. The suppressors, like I said, these are the ones that basically tell everybody else to stand down. We have eliminated the threat. Everything's good. You don't need to be on high alert anymore. Everybody chill out. Because like I said, an overactive immune system can do even more damage than the disease in the first place. People with psoriasis, unfortunately their immune system is attacking their skin, and that's why they get, these huge plaques all over, and they're constantly, covered in those. It's because their immune system is like, that's not a part of us, and it attacks your own skin, and then in response you make all these plaques, and it's itchy as insane as heck. So, that's your immune system attacking your own integumentary system. Not cool. But that's also what COVID kind of did. COVID came in and made, even though he's kind of a weak-looking little jerk, he came in and actually overexcited people's immune systems. See, what happened is he attacks lung cells. That's why, but not only is he attacking the lung cells, but he super excites your immune system into also attacking your lung cells. They kind of go enemy blind. So they're like fighting the COVID, but then COVID goes, hey, these are enemies too, and it's actually your lung cells. So COVID was so bad because it was literally not only the virus attacking, but the virus prompting your immune system to go in haywire and start attacking your lungs as well. So it wasn't just a virus attacking, everything was attacking you. So that's why COVID was so bad. So, naughty virus. It was using our own immune system against us. Rude. So now I want to talk about vaccines. And a lot of people, I don't think, understand enough about vaccines. And that's why I want to talk about the different ways we've come up with vaccines. So the first person to really come up with a working vaccine was, interestingly enough, some people go, Louis Pasteur with rabies? No, it actually was Edward Jenner. He was one of the first ones that kind of studied this. And he noticed that, again, one of the major diseases running around that we've had since the dawn of ever since we created civilization, period, like I'm talking about Euphrates River Valley kind of level stuff, is smallpox. But he noticed that people who work with cows, dairy maids, would work with cows and they'd get infected with cowpox, which is very similar, but they'd heal and they'd be fine. And then they were immune to smallpox. They never got smallpox. And he was like, are they related? Now we can say yes, because we've done a whole bunch of viral DNA testing to figure out the histories of these viruses and where they came from. It's actually really fascinating. So what he did is he took the Sarah Nelms, and she took, out of the pustules. I'm not kidding you. She had cowpox, and she had the pustules, and he literally took liquid out of the pustules and injected it in some poor kid named James Phipps. And then he was inoculated with cowpox pus from her. Delicious. Oh, God. So anyway, Phipps falls ill with a mild case of cowpox. And then scabs were taken from a smallpox patient. Yeah, this was before ethics, by the way. And then Phipps is inoculated with the scabs of smallpox. So literally they took that and injected it in him. And Phipps is unaffected. He doesn't get smallpox because he already had cowpox. And because they're so similarly related, his immune system had already remembered, and smallpox wasn't going to get him. So he was like, so smallpox and cowpox are related. Keep in mind, this was way before we even knew what DNA was. So, yeah, so that was Edward Jenner. So he was kind of like the first one to sit there and say, all right, something's going on here. Next up is Louis Pasteur. He basically was doing research on rabies. And the rabies disease was actually pretty bad. It was taking out a lot of people. Keep in mind, Louis Pasteur was in France. And he was coming up with this vaccine, which is an attenuated vaccine, which is basically a weakened virus. It's alive. The virus is alive, but it's it's been weakened, so it's not dead. Because Pasteur found out if you kill the virus, then there's no immune response. The immune system is just like, it's dead. Why did you stick that in here, dude? So it wasn't until way later that we figured out how to use a dead virus to trigger an immune response. And so that is basically, and the story goes, is him and his assistant had the vaccine ready, but they needed somebody to test it on. Now, granted, this was still back in the 1800s, so it was still kind of questionable ethics, really questionable ethics, and this is actually why his person left him, his assistant, who was also a doctor, because he got mad at what Pasteur was about to do. There was a boy who was savaged by a rabies dog, and him and his mother walked for miles to Paris to meet with Pasteur. They knew the kid had no chance. But they literally, this kid who was savaged, I mean, his leg was just destroyed. They know they didn't have a lot of time. Literally, his mother grabbed his stuff, packed him up, and they walked from their town for days, which is already wow, just to get to Pasteur to see if they could save his life. So she comes in and she's like, please, please, please. He was bitten by a dog. He was savaged. Please, please save him. He's going to die of rabies if nobody treats him. And Pasteur goes, aha, I have the vaccine. And they haven't tested it yet. They hadn't tested it at all. And his, like I said, his assistant went, no, you're not going to. And Pasteur was like, yeah, I'm gonna so give it to this kid. And his assistant's like, dude, we have not tested this. We have not tested this on humans. You're gambling with that child's life. Are you mad? This isn't honorable at all. You can't do that. And Pasteur was like, yeah, I can. And he was like, you're insane. We don't even know if it's going to do anything or if it's going to make the kid die faster. And Pasteur was like, And the guy quit working with Pasteur in protest, but it worked out for the kid and for Pasteur, unfortunately, as it worked. Fortunately, unfortunately, I don't know. I don't know where to come on that one. Yeah, it made him famous. That's how we got the vaccine for rabies. But it's also really kind of makes you go, because he wasn't really doing it to save the kid's life. He was doing it to see if the vaccine worked. It isn't like we have no choice. It isn't like, an episode of ER or whatever other shows are out there that I haven't watched in years. What's that one with the girl and the mixed sexy or whatever the heck it is? Anyway, whatever. So it wasn't like he was sitting there going, well, it's the only way to save this child's life. It's the only way to do this. No, he was just like, he just wanted to see if it worked. The kid was just a stepping stone to him, which is why the guy threw a fit. So that's attenuated vaccines, and that's the ones we could make for quite a while until we figured out with Jonas Salk against polio. Polio is insane, and when people get on their anti-vaxxer at me, I like to pull out the polio card because it's an inactivated vaccine. So Jonas Salk figured out how to basically use a killed virus to trigger an immune response. Because before that, we could only use weakened. Because dead ones didn't do anything. But luckily, Jonas Salk figured out a way to use inactivated ones or dead ones to trigger the immune response. And thank God it saved us from polio. Polio is insane because it slowly, completely, and utterly, disables the person. That's why on the Oval Office, one of the very famous desks there has a little door. It didn't used to have a door because it had that for FDR, who had polio, and he was confined to a wheelchair, but he didn't want anybody to know. So they took pictures with somebody, with the stand standing him up. They did everything in their power to make sure that nobody knew he was in a wheelchair because of polio. And it's actually kind of interesting. We think his wife technically was the first female president because for a while he was dying of polio, and his wife kind of took over. Anyway, it's kind of interesting. So anyway, I want to show you the iron lungs. And this just kills me. Thank God we don't have these anymore, and this is because of the polio vaccine. These are all iron lungs. These are iron lungs for children. This is a children's ward right here. Here's a child in an iron lung. Yeah, this could be your kids, your brothers, your sisters without the polio vaccine, because this is what happens. They get paralyzed, and what happens, unfortunately, is they cannot breathe on their own. And the iron lung, what it does is really clever. It just makes a kind of a zone, so where that way it makes the pressure rise and fall and makes you breathe along with it, because that's how our lungs work. We'll talk more about that when we get into the respiratory system. But you don't see this anymore, do you? You don't see wards filled with iron lungs. Actually, the surviving people are having that need iron lungs, which are very few, are having the worst time trying to find parts for their iron lungs because they're breaking down. because we don't need them anymore. Nobody's manufacturing parts. It's actually one of the few things, not few things, I love 3D printing, but 3D printing is actually helping these people that are still reliant on iron lungs. But there's so few iron lungs because of the polio vaccine. So, and my mom remembers getting it. She didn't get a shot. They just put a drop on a sugar cube, and that's how you got the polio vaccine. It was literally just a drop of liquid on a sugar cube, and you ate the sugar cube. There, bada bing, bada boom, you got the polio vaccine. So, if it wasn't for Jonas Salk, polio was just ripping through humans. Without that vaccine, I can't imagine having my son being stuck in that for the rest of their lives, dependent on that to breathe, so they can sleep through the night and not, stop breathing. That's why I get so annoyed. Vaccines are, out of all the amazing things that we have invented as a collective species, vaccines are the most important in our survival. If it wasn't for vaccines, go look up how many are death rates for kids before vaccines compared to now. It's insane. So that's why I get really annoyed. And this is just me, you can debate with me or argue with me if you so choose. But this is, and I'm not going to put this on a test or anything like that. This is just me on my soapbox. But, vaccines are insanely important. If it wasn't for vaccines, we wouldn't have the quality of life that we have right now. It is the single most greatest invention of the human race is a vaccine. And you can't really convince me otherwise of that. It's our way to fight against something that would take us out. And it's just insanely clever how our immune system can learn and how we're using weakened or dead viruses to force it to learn faster. And that's literally what we're doing. We're just giving our immune systems a crash course on how to deal with these viruses before they ever hit the real thing, which is just beautiful. Now, the newer ones that we're dealing with when we came up, the ones that you're like, oh yeah, why? Well, and one of the arguments was, it's like, oh God, the COVID vaccine, it came out so fast. Well, that's actually because we were kind of working on a version of what we came up with to fight COVID already before that. We were actually using it to fight HIV, of all things. So we came up with some vaccines that we were using against other viruses that just so happened we had the technology. Nobody was, reporting it in the news like we do, because nobody was really, how many of you read scientific papers all the time? Yeah. And not a lot of scientific papers always make it into the news as big news. So they were working on different types of vaccines for a while now. This wasn't something that just came out of thin air. We had already been using it for things like HIV. We'd already been looking at it for other things like, when we saw SARS pop up, because COVID is related to the SARS viruses. They're out of the same family. There's 3 different families of viruses that can attack your lungs, which is the influenza family, which is where all the flus come out of, which came from birds. Stupid birds. Anyway, and then the rhinoviruses, which are all the cold type ones. And then there's the SARS line, which the SARS lineage is where all the different SARS ones, which were popping up a lot in the Asian countries. And then COVID. So FYI, COVID's out of the SARS land. So anyway, so what we did with this is we were like, all right, we can't weaken it because it still explodes. Because remember what I said COVID does is it excites your immune system into attacking your lung cells as well as attacking your lungs. So if we gave you a weakened version, it would blow up into the same mess. If we gave you a dead version, it was one of the ones where the body just goes, eh. So we had to come up with a new way, and basically we figured out this. It's like, wait a second, these things right here, these antigens, these are the things that stimulate the stimulate the immune system. Why don't we just cut these off and not even use the virus itself, so we take the risk of the virus out? Why don't we just shave the viruses of all these antigens? And we did. And that's literally what a subunit vaccine is. That's what all these COVID-19 things are. We literally just took COVID-19, shaved these proteins off, stuck them in, some preserving liquid, and triggered them, put them into our body. So that way, again, a macrophage is wandering around, and these things are floating by, and they're like, oh, that's cool. I'll stick it on and go show a T cell. Bada bing, bada boom. It triggers the immune system response without having the whole virus. So it's clever. We just shaved them bald and handed our body these things, which is what the antibodies are made off of. And it triggered our immune system, and then our body knew it without having to put the whole virus in. So we basically just took the one thing that our immune system's interested in, these proteins, and triggered an immune response without the virus, just these things. And that way, when the virus attached to these things come in, our immune system is already like, kill it. Now, the next level we're looking at is nucleic acid vaccines. So it's basically what we do is we actually take the viral DNA and the viral RNA to literally take it and make it so our body can already manufacture these parts of the virus to trigger the immune response. So in other words, we teach our body to make parts of the virus, to make the antigens, to trigger our immune response. So again, rabies, polio, COVID-19, future. Like I said, vaccines are amazing and fascinating, and I wanted to talk about them, even though your book really doesn't go into them, because I feel it's something that everybody should know how a vaccine works, and how it triggers our B cells and our T cells, and then we remember it later on. Like I said, vaccines are just kind of like an accelerated course to learn a virus before you actually get the virus. So you have that secondary immune response, as we saw back here, where it jumps and you don't get sick. So instead of having to go through this, the vaccine teaches our immune system, so we just instantly go to this without having to waste time and our life getting sick. I hope that makes sense. I hope you don't mind me getting off on my little tangents too much. It's just, I find this fascinating, and I hope you found it fascinating as well, and how, vaccines are so important to everyday life here on Earth. And yay, vaccines. All right, again, here's another good one, the bacteriophage. It's talking about the deadliest being on Earth, which is bacteriophages, but we're also looking at using them, which is a type of virus. Here's a bacteriophage. I have a plushy one. Of course I have a plushy one. These guys, as their name suggests, they only attack bacteria, which is a good thing. But we're thinking about using these also to attack bacteria for bacterial infections. We actually healed a guy. He was infected with a really bad bacteria, that one that all the hospitals dread because it's all antibacterial resistant and there's just no drugs that can kill it. Yeah, he had that. And we were like, oh God, he's going to die. So we went to him and said, listen, we have this kind of interesting thing. If you don't mind being injected with this type of bacteriophage, it could probably kill off the bacteria, and it's not interested in you. And it did. It worked. He lived. We saved his life by the use of a virus to kill the bacteria that was killing him. And he lived. And that's what possibly in the future we could use these two, because like I said, what usually gets us sick in a disease kind of way is bacteria or viruses. And these guys have been fighting wars since the dawn of life on Earth, and we're now learning how they do it. It's kind of like a crazy arms race. So we are looking at using viruses to destroy bacterial infections that our drugs just can't handle. And so far, it's looking really promising. Like I said, it saved one guy's life. And that's what this video goes over. It goes over the war between bacteriophages and bacteria, and how we're thankfully just on the sidelines looking at it going, we could use this. So it's a good video. I like Kursha. I don't know how to say their channel name. I don't think anybody does. No, don't start. Anyway, so good video. Highly recommend. Just kind of interesting to watch. So there you go. That's my rant on bacteria. That's my explanation of how that works, and good to do. So thank you so much, and I'll see you next week. Bye.